Today's I would like to introduce our speaker. I'm delighted to have with us today Owen Rambow from Stony Brook University, my colleague in my department, and we are delighted to have joined our department. In fact, he just completed his first semester, I believe, at the Stony Brook Linguistics Department. We're absolutely delighted about that. Professor Rambow's interests focused on natural language processing and computational linguistics. He's interested in the nuts and bolts of language that you know, morphology and syntax, and how language is used in context. He has a PhD in computer and information sciences from the University of Pennsylvania. And before he was at Stony Brook, he was working in industry at various different companies. He worked at AT&T. He's also worked at Columbia University, and more recently at a startup called, I believe, Elemental Cognition, to try to develop software for language understanding. You can read more about him on the Stony Brook website, but that's all I would like to say, just to welcome Owen Rambow and take it away.
Thank you very much. Let me share screen here. So thank you, John, for this very nice introduction, and also for inviting me. And thanks, Vinny, for doing the technical facilitation. And thanks to all of you in the audience for coming out. And I know that for some of you, it's actually very late. So I appreciate your interest. What I want to talk about is the following. I basically want to talk about deep text understanding and a particular aspect of that, which is semantic parsing. But I have added a very short section at the beginning to talk about what computational linguistics and NLP, natural language processing, are. And I will start out with that. Then I will try to define deep text understanding. I will list various aspects of sentence meaning, and then very briefly summarize some experiments we did on semantic parsing. But that is not the emphasis of this talk. So what is computational linguistics? This is my view. It might not be, it might not represent consensus in the field, but the way I see it is computational linguistics has a goal of understanding the formal mechanisms of how language, of human language, and of linguistic theories. So there's a computational aspect of that, which is understanding how human language processing works, how we humans process language. And in addition, competence theories, such as syntactic theory, might have a computational element to it, and we want to understand that computational element. But there's a second side, which is not computational, but simply formal. We want to understand what the formalisms are that humans are using, that linguists are using to describe human languages. And what's important is that it's not a subdiscipline of linguistics like phonology or sociolinguistics. Rather, computational linguistics represents a choice of methods. And then these methods, namely the computational and formal analyses, can be applied to any subdiscipline of linguistics, including, say, phonology or sociolinguistics. And I also want to point out that computational is not one of the options in the paradigm of descriptive and theoretical linguistics. So where descriptive linguistics means we're describing the linguistic data, theoretical linguistics uses linguistic data to devise theories, and these theories then make predictions about the data, and the predictions might be false or true, and if they're false, then we will go back and revise our theories. Computational linguistics can be either descriptive or theoretical, so it's orthogonal to that distinction. Now, what is natural language processing? I see NLP, so I'll refer to it by its abbreviation NLP, I see it simply as the engineering discipline of computational linguistics. What is engineering? Wikipedia defines it as the use of scientific principles to design and build machine structures and other items. And the important things here are, first of all, using scientific principles. So engineering is interested in science, but its goal is not to extend science, but rather to build something useful. And so in the case of NLP, the goal is to build machines that process human language. And machines, of course, here means computer programs. And I just want to use an example, not from NLP, but from mechanical engineering. We want to build a bridge. And so we can't just sort of start putting stones on top of each other. We need to understand the chemistry of the materials we are using, and we need the physics, we need to understand the physics of the structures we will construct. And perhaps we even need to understand science of managing so that we can actually carry out a huge project. So engineering is indebted to science. And similarly, if we build a machine that processes human language, we will need to look to linguistics to understand human language. But I would like to point out that though there is this dependency from science, so engineering depends on science, but sometimes engineering actually drives science. A well-known example is moon landing. Another example is electric cars. So that is currently of great interest related to climate change and other concerns. And there's a lot of interesting computational research at Stony Brook right now driven by this interest in better batteries, because good electrical cars require better batteries. And so there's computational modeling in the chemistry department of the interactions of ions, for example. And I think this is a clear example where sometimes engineering says, hey, wait a minute, we need to understand this area. Excuse me. So this is an area where, in general, sometimes I think engineering will say, hey, science, we need to address these issues. You need to start researching here. And finally, I just want to point out that science engineering is not really a binary distinction at all. It is a continuum. Most of the work is somewhere in between, especially in computational linguistics. Okay, now going on to deep text understanding, trying to understand what it is and how to measure it. And this section is based on an ACL paper with my former colleagues from the company I worked at, Elemental Cognition, and deep text understanding and machine reading comprehension I will be taking as synonyms. Now, this is not a new topic in NLP. There are many existing benchmarks for text understanding. But the question that we asked in that paper is, do they actually measure the performance of systems for specific tasks? These tasks can be things like answer questions about a clinical timeline, assess compliance with regulations or legal obligations, read a description of a game world and adjust a character's response, and so on. So specific tasks that we have. So in this section, I will first of all summarize what is missing from these tests. I will present our proposal for analyzing stories with what we call a template of understanding. And I will show that the state-of-the-art systems fall short on our story template of understanding. So SOTA is the NLP abbreviation for state-of-the-art. There are many existing text understanding benchmarks. Many of them have the problem that they are artificially easy, meaning that a system, you can very easily train a computer program to just do very well on them. Obviously, we don't want that. A second problem is this third column over here, which is that they omit obvious questions. This is far less obvious to understand, but when we read a text as humans, there are certain things we immediately understand. If it says, Mona drove to the shop, we immediately understand that she is, after driving to the shop, she is at the shop. Computers don't necessarily know that. But when we ask humans to write questions for us, they will not necessarily ask, where is Mona after driving to the shop? Because it is so obvious to us humans. So this issue of omitting obvious questions is a big problem with many benchmarks. And another problem is that they often focus on difficult cases rather than uncovering the content broadly. And that is, of course, interesting. And that is often how scientists work. A theoretical linguist doesn't work on all of syntax at once. She will choose a particular topic, such as, I don't know, reflexives in Korean or whatever, and then drill down. But if we're trying to understand whether a system understands a story, we need to cover everything. We can't just drill down. So what we propose is to establish clearly what content is needed in order to evaluate whether a system has a deep understanding of a story. And by content here, we mean the information expressed or implied or even relied on by the story or by a passage. So let me make that more concrete, and I'll introduce our notion of template of understanding. We will start out by choosing a genre, and I'll say more about that in the next slide. We will then characterize, given the genre, what type of info needs to be extracted. And this characterization of the type of info is what we call a template of understanding. We then select some text, and then we determine the relevant passage content with respect to our template of understanding. And then we design tests to see whether a system actually gets the content that we decided is needed. And the genre we're going to choose is stories. And in fact, we worked on stories for first graders, so 6-year-old kids, because that's about how far we can hope to get with computer understanding at this point. But in addition, stories are actually really useful for many applications. And in addition, stories have the nice advantage that they have been studied by cognitive scientists, so that we have strong independent evidence for what content applications will need. And cognitive science research has shown that what humans retain from stories can be characterized along 4 dimensions, namely locations, timelines, causes, and motivations. So let's look at those in a bit more detail. These 4 dimensions will be our clusters of questions for our template of understanding. Spatial means where are the entities mentioned in the story, positioned in the story, and how are they oriented throughout the story. Temporal means what events and states occur and with what timing. Causal means how do events or states mechanistically lead to other events or states described or implied by the text. And motivational is how do agents' beliefs, desires, goals, and emotions lead to their actions. So motivational and causal are related, but motivational is that part of causal which relates to human agents or animal agents, hidden states, or cognitive states. So our evaluation approach is to take the template of understanding and then to explicitly annotating answers for a given story, and that's what we call the record of understanding. So here's a simple story fragment. One day it was raining. When Allie arrived, Rover ran out the front door. He barked when he felt the rain. He ran right back inside. Not a terribly interesting story, but hard for computers and apparently interesting to first graders. And so here I'm just writing out some of the entries that our annotators produced for this story. Spatial, Rover is in the yard from when he runs out the door until he runs inside. Rover is in the house from when he runs inside until the end of the story. And I want to emphasize this is not the full spatial description. There's a lot more because, for instance, we haven't mentioned Allie at all yet. Temporal, Allie arrives just before Rover runs outside and it is still raining at the end of the story. And then motivational, this gets a bit more complicated. And I don't want to spend a lot of time on this, but just give you a flavor. So Rover runs inside rather than staying put because Rover has a goal of not getting rained on. Why does he have that goal? Because Rover is getting rained on, and Rover does not like getting rained on. And why is Rover getting rained on? Because it is raining. And when it is raining, things that are outside tend to get rained on, whereas things inside do not. And so, given this goal, he forms a plan to achieve his goal, as rational agents, including dogs, do. And if he runs inside, he will be inside. And if Rover is inside, he will not get rained on. And when it is raining, things that are inside tend to not get rained on. That is the reason why he will not get rained on. So what you sort of see is we try to ask why questions repeatedly, a little bit like 6-year-olds do, until we get to the real basis. These kind of questions are things that human can answer easily, computers cannot. So how do we implement an actual evaluation? In NLP, we want to have different systems. We want to compare them against a gold standard. Our gold standard is our record of understanding. how do we actually implement this so that we can compare different systems? If you're interested in this very NLP-ish question, I'm happy to talk about in the question period. And one last point here about this deep story understanding, the state-of-the-art systems fall short on our story template of understanding. And we're going to do a case study using the race stories. So as I mentioned at the outset, there are many, many different data sets that are being used currently to test whether computers can understand language. This is one of them. It is particularly interesting for us because they are stories. They're actually stories used in English exams for middle and high school students in China, in the People's Republic of China. And the students are aged 12 to 18. And the exam consists of texts and questions about the text. This Lai et al. Paper 2017, they presented a very simple system that performed at a level of 44%, whereas humans get 95% correct. And these humans are not necessarily the Chinese middle school students. These are native English speakers who answer these questions. And we're using just 2 stories. And what we did is, so this is, by the way, where race falls in this table. These are tests designed for humans. And what we did is we took the story and the answer and the questions and the answer key and turned it into a multiple choice data set, because that is how many systems can handle question answerings. So first of all, we created our record of understanding, created the specific answers to the spatial, temporal, causal, and motivational questions, and then we turned it into multiple choice questions. So just to give one example, I'm not going to give you the whole story, but what actually happened when Mr. Green and the man drove together. And then there are 4 choices. They came to a small house, they came to a hotel, they traveled around the country, they stopped several times at the side of the road. And the correct answer is A. So then we trained a system. We used the XLNet system, and this is actually I tell you, this is not our system. This is a system we're going to compare against, which is the state of the art. It is called XLNet, presented by Yang et al. In their 2019 paper. So in this field, things develop rapidly, so probably performance is better now, but this analysis makes a point. They use a transformer-based language model, as people do nowadays, which is XLNet. It is trained on the books corpus, which is a very large collection of English language literature, and English Wikipedia, which we all know. And it performed at a level of 82% on the race task, which was one of the best performing systems. And notice that within 2 years of development, it went up from 44%. So this 82% is a performance on the race task, not on our task. Let's look at how XLNet performed on our task. So over here, the first bunch of 3 results is all the questions. How did it perform on all the questions? Humans perform at 96%. That is very similar to the actual race task, which had different questions from ours. Chance is very low because it's a multiple choice task with multiple answers. So chance is only 15%. And the system did better than chance, but it did very far from human. And it also did very far from 88%. So the system that was trained to understand stories is good at answering the questions that were in the original race exams, but it is bad at answering the questions that that we deem to represent deep story understanding. And we can divide it up here by the spatial and temporal questions and the motivational and causal questions. And to our surprise, we actually expected the causal and motivational questions to perform worse, but across the board, both the system and the humans performed worse on the spatial and temporal. We don't have an explanation for that at this point. So the point here is, a summary of this section is, we can define what we might mean by deep understanding of text based on the templates of understanding. we feel that deep understanding of text has been neglected in the field of natural language processing as a task. And templates of understanding represents a knowledge that is relevant to extract for a particular text genre, namely stories. But stories are in fact ubiquitous across many applications and are therefore really important. And current machine learning technology may produce good results on some existing text understanding tests, but then they just fail on our template of understanding. Well, they don't fail, but they do much, much worse. And in the future, we imagine that our templates of understanding can serve as a basis for cross-system evaluation. Okay, now let me move on to the next section of this talk, which is about the aspects of sentence meaning. So just now in this section, I was talking about understanding the whole text. Now I will drill down to single sentences. The idea why we're talking about single sentences is that we can construct an understanding of the whole text by processing each sentence and then build up a meaning of the text by creating the meaning of each sentence. And the deep understanding, which is what I was just talking about, will then come from the meaning of all sentences in the text, plus some common sense and background knowledge, plus inference over all of this. But that is not what I will talk about in this section. Instead, the goal of this section is just simply to highlight the complexity of the task of simply extracting the sentence meaning, which is this first bullet here, without even talking about common sense and background knowledge and inference, which are extremely complex. So I will now list several aspects of sentence meaning and just comment on the state of the art in NLP and how it relates to linguistics. And I will start with the notion of word sense. So the same word, this is extremely well known and it's true for every single language, the same word can have different meanings. So look at the word bought. John bought a car, it's a commercial transaction. It means he paid some money for it. John bought the story means he accepted the truth of the story. No money changed hands. And I actually don't know the etymology of where this use of buy comes from. I sort of have the sense it's fairly recent, but that might be wrong. So in order to understand a story, clearly we must know what the meaning of bought is. So John bought a car, it's highly unlikely that in fact, it's meaningless to say that the meaning of bought here is that he accepts the truth of the car, that car is not of truth. But in John bought the story, in the right context, it actually could mean that, you know, someone recommended a story to him and he went to a bookstore and bought the story. So it could mean a commercial transaction. And the approach to word sense disambiguation is, in natural language processing, is to use a context. Now, for NLP to do word sense disambiguation, we need an inventory of word senses and of annotated corpora to do the machine learning. And we have we have several such inventories. I will talk about that a bit more. And we do have annotated corpora. And this is a very active area of NLP because it is so fundamental for understanding. The next aspect is semantic predicate argument structure. Basically, who did what to whom. So let's assume we have a meaning for a predicate. So the predicate is typically a verb, and the examples just now was bought. Can we determine how other elements in the sentence relate to it? So here's one of the standard examples. John bought a car for $3,000 from his sister. John paid $3,000 for a car to his sister. John's sister sold him a car for $3,000. For all of these sentences, there are different predicates, bought, paid, and sold. But in all of these cases, they refer to a commercial transaction. And in all the sentences, the buyer is John, the seller is his sister, the price is $3,000. And I apologize, I forgot to write down, the goods that changed hands is a car. So that is what we want to do in semantic predicate argument structure detection. We want to determine these roles. Who's the buyer, who's the seller, who's the price, what is the goods. And word sense disambiguation, which I just talked about, and the semantic predicate argument structure determination is together what we call semantic parsing. And I'll discuss that in more detail in the last section of the talk. A next very important aspect, which is also crucial for any real natural language processing to be successful, is co-reference. So we need to resolve the co-reference between noun phrases in a text. There are, cases where we can do that very easily. Paul was poor, John bought him a car. The grammar of English tells us that him cannot refer to John and must refer to Paul. Paul was poor, John bought himself a car. Himself must refer to John, it cannot refer to Paul. But oftentimes it's more complicated. So consider the following pair of sentences, which come from Seidner's 79 thesis. I took my dog to the vet yesterday, he bit him in the hand. And I took my dog to the vet yesterday, he gave him an injection. Now, first of all, notice that we understand those two mini texts, two sentence texts immediately. There's no sort of issue of, wait, what, who did what to whom? We as humans get it immediately. And secondly, note that the he and the him here exactly flip co-reference. Here it is a dog that does a biting of the vet, and here it is a vet who gives the dog an injection. So these sentences have very, very similar syntactic structure, and the syntactic structure does not tell us who he refers to and who him refers to. We must use world knowledge. Dogs do biting and vets do injections. So this first example is of great interest in theoretical syntax. The second example doesn't have much interest in theoretical syntax because there is the emphasis on possible interpretations and not on how to choose the right one. But then for NLP, in order to understand a text, we have to know how to choose the right one, who bit whom. It is a very active area of research in NLP with many annotated corpora in many languages. And I just want to mention in passing that event co-reference is part of co-reference, but is much more complex. So if we have a mini text of the type, Liam left for Limerick, his departure devastated us, then his departure is co-referential with the whole sentence, Liam left for Limerick. That is what his departure means. And in order to understand this two-sentence text, we need to know that his departure refers to Liam leaving for Limerick. We also need to know that his refers to Liam, but that's not all we need to know. Then let me mention quantifier scope. So this is something that linguists know about and NLP people typically do not. So I probably don't need to tell this audience that the scope of quantifiers with respect to each other is constrained by syntax, but not determined. So if we have a sentence like every student learned a song from a local resident, we have at least 4 interpretations. I think we have exactly 4 interpretations. I don't think I missed one here. And it is, of course, this question of, given a sentence, what are the possible semantic interpretations, including quantifier scope, is a focus of interest in linguistic semantics. And once again, the emphasis is on possible interpretations, not on how to choose the right one in context. And quantifier scope, unlike pronoun resolution, is not an active area of research. Although it might be important for inference. For example, if we have a sentence like 3 students learned a song from a local resident, and part of the deep story understanding is to realize that 3 songs were learned, but the computer might not be able to disambiguate the quantifiers correctly. And of course, once we throw in the event variable, things get more complicated. So if we have a sentence like 3 men carried 4 pianos, and we ask how many carrying events were there, there can be between 1 and 12 carrying events. One possible reason why NLP hasn't paid much attention to this is that it is not clear that we always fully disambiguate this in human communication. Sometimes we do, sometimes we don't. If I tell you 3 men carried 4 pianos, and in the context it's irrelevant how many carrying events happened, maybe it just remains underspecified. And I think the last thing I want to mention is implicatures. An implicature is not a logical inference, but a conclusion the audience can draw based on what was not said. So if I tell you that I bought 2 pencils, you know that I didn't buy 3 pencils. It is not a logical consequence, because if I did buy 3 pencils, it would also be true that I bought 2 pencils. But rather, it comes from conversational logic, namely that if I had bought 3 pencils, I would have told you so. And that is based on Grice's maxims. A more interesting example is something like Sandy as a friend. If I tell you that Sandy is a friend, perhaps introducing Sandy to you, you will infer that Sandy is not my lover or my spouse. Because if he or she were, I would have told you so. And contrast that with Sandy as a bore, or Sandy as a psychologist, or Sandy as Senegalese. And all of these sentences, there is no additional implicature. We can't infer anything else from that. So it's only certain types of words that allows us implicature. On the other hand, it is very important. So if in a story it says Sandy is a friend, and the computer doesn't know that Sandy is not my lover or my spouse, the computer might misunderstand the story. As I mentioned, this is based on assumptions about rational conversation, Grice's maxims, and it is in fact studied in linguistic pragmatics. It contributes important aspects of meaning, but it is not an active area of natural language processing, though there is some very interesting formal work on modeling, and it might become more important in the near future. Oh, sorry, this was not the last point. The last point is modeling cognitive state, which is actually one I'm specifically interested in. So when we use language in context in communication, we don't only convey to each other propositional content, who did what to whom. That's not all it's about. We also convey our attitudes towards the propositional content that we're conveying. And these propositional attitudes that I'm interested in here are belief and sentiment. So let's look at some examples to make this clear. If I tell you John will leave tomorrow, I am committing to the fact that I believe fully that John will leave tomorrow. If I later tell you, well, maybe he won't leave tomorrow, then you can challenge me and say, wait a minute, you just said he will leave tomorrow. So that I'm representing that here by saying that the speaker level of belief is 1. So the idea is there's a scale from -1, meaning completely disbelief, to 1, meaning completely believe. And here in the sentiment column, well, I'm not telling you anything about my sentiment about John leaving tomorrow, so it's just open. And then if I say John may leave tomorrow, then I'm no longer telling you that I'm certain about it. Maybe my level of belief is only 50%, 0.5. Again, I'm not telling you anything about sentiment. And this has been called non-committed belief, because if I say John may leave tomorrow, and then later say, well, maybe John won't leave tomorrow, you can't challenge me, right? Because I didn't commit to John leaving tomorrow. I just raised it as a possibility. And then if we go to embedded sentences, things get even more interesting. I hope John will leave tomorrow. The most important aspect of this is a sentiment. I'm expressing a very positive sentiment towards John leaving tomorrow. I'm sick of him. I want him to get out. This is generic John. And but interestingly, hope also tells the listener something about my belief level, because I'm not certain whether he will leave tomorrow or not. If I were certain, if I'm certain that John will leave tomorrow, I can't say, I hope John will leave tomorrow. I would say something like, I'm glad John will leave tomorrow. So this sentence here tells us something about the speaker's belief and sentiment towards the John leaving event. And then these last 2 examples have been studied extensively in the linguistic literature. Mary claims John will leave tomorrow. Well, I'm telling you what Mary believes, but my belief is slightly negative about John leaving tomorrow, because this verb claim in English implies that, well, that's what Mary says, but I don't quite believe her. And there's no sentiment information. But if instead of saying claims, I'd say, Mary says John will leave tomorrow, I'm not telling you anything about my beliefs. I'm not telling you anything about my sentiments. I'm just telling you about Mary's belief. So there's a question mark in both columns. So basically what this modeling cognitive state is about is, given a sentence, determine these 2 columns. There has been some work in linguistic semantics on belief, where it has been called factivity and some other terms. However, there's been a lot more work in artificial intelligence and in cognitive science and in natural language processing. The NLP work has concentrated in the last 10 years or so, mainly on sentiment, and this was driven by commercial interests. Companies want to know what people are saying about their products. So there are tons of papers about taking a tweet about a product and determining is it positive or negative. And modeling cognitive state, not sentiment analysis, but the broader topic, is an active area of interest for me. And if you're interested in that, do shoot me an email, please, or ask me a question. So in the remaining time, I'm going to talk about semantic parsing now. So semantic parsing of a sentence, what are the steps? First of all, we have to choose an ontology which has argument structure. I'm going to talk about ontologies shortly. We have to determine the content words of the sentence. And this is sort of non-trivial because most or all languages have multi-word expressions, like kick the bucket is a famous example, where we don't want to determine what kick means and what bucket means. We want to determine what kick the bucket means. So let's disregard that problem. And for each of these content words, which are also called triggers now, we want to do word sense disambiguation, which meaning of kick, which meaning of bucket. We want to identify the semantic arguments that the trigger has as text spans. And then we want to identify the semantic role label, such as, you saw earlier, the buyer, the seller, the price, the goods. And then when we have a semantic parse for one trigger, in theory, all of the semantic parses for the triggers are assembled into a single structure, which will probably not be a simple tree, but a directed acyclic graph or something more complex. This is not actually always done in natural language processing. And I want to just mention here abstract meaning representation as a very nice example, which does create a single structure representing the meaning of a whole text. And it is based on prop bank, which we will talk about shortly. So this is essentially what semantic parsing is as an NLP problem. Now let's talk about what an ontology is. The term ontology means an inventory of what there is, from Greek ontos, being, or that which is. And it consists of term-designated classes of things or situations or events, such as commercial transaction, and relations between the terms, and is a relation or part of relation or other relations that might be ontology specific. And then there's additional information, namely this argument structure that we're interested in. Someone gives something to someone, or someone buys something from someone for some amount of money. And there can be additional information. So if we, for instance, have an entry for a penguin, there can be an attribute. Penguins are white and black. Penguins have a color. And then there can be a typical attribute value for a penguin, namely a penguin is typically white and black, and an elephant is typically gray. And this is sort of then getting into encyclopedic knowledge, and it's sometimes a little bit hard to distinguish between ontological knowledge, which is supposed to be word knowledge, from encyclopedic knowledge or world knowledge. So basically, an ontology represents a massive effort in descriptive lexical semantics. And semanticists often do not like lexical semantics because there is not much theoretical content. But creating such an ontology is often a major contribution to NLP. And I'm going to discuss two ontologies that have been used widely in NLP. The first is prop bank, developed for the last 15 years by Martha Palmer and her colleagues, originally at the University of Pennsylvania, subsequently at Colorado. She has espoused a traditional lexicographic approach to word sense. So for each word, the senses are listed, and the senses of words are called predicates, or also in prop banks are called role sets, because each predicate will have its own set of semantic roles. And the semantic roles are represented using arc and then some suffix to it. But these, even though there's a small set of arc labels, in fact, a lot of the arc labels are predicate specific. So if you have an arc 2 for buy and an arc 2 for see, it might not have the same meaning. And then there are also adjunct roles for time, place, and manner that are identical across predicates. Let's delve into an example. So this is by again. There are two role sets that are relevant to our examples here. One is purchase. So this is just a gloss to make it easy to recognize what is being meant here. And we have these 5 argument roles here: the buyer, the thing bought, the seller, the price paid, and the person for whom it was bought, the benefactor. And so the name of these roles is arc 0, 1, 2, 3, 4, and then there's a hyphen which makes clear what this is. So this is agentive, theme, direction. Gosh, I forget what VSP is, and this is goal. And then the other meaning is accept as truth. That is, he bought the story. There are only 2 rules: the believer and the thing believed. And just to compare things, here's a different one: bring, a meaning for bring, which is carry along with, the standard meaning of bring. And you'll see here that arc 0 and arc 1 in both cases are agent and theme, but then the order of the goal and direction and so on are switched. So here arc 2 is direction, here arc 4 is direction. So if you work with ProcBank, beware of attributing too much meaning to arc 2 and arc 3 and arc 4. And here's another such example. The second ontology I want to talk about is FrameNet, based on, it was conceived of by Chuck Fillmore in the late 90s. And it has a different approach from ProcBank. ProcBank starts with words and tries to identify meanings. FrameNet starts with semantic situations, such as a commercial transaction, and asks how language can express it, and then finds all of the verbs or nouns, words in general, that refer to a commercial transaction. And we already saw these examples: bought, paid, sold, but we can also have cost, or we can have a different argument structure of bought, $3,000 bought John a car. And here is, this is obviously a screenshot from the online version of FrameNet, meaning one of by is commercial transaction, and here are these goals. And here's the other meaning of by, which is fall for. A victim comes to have incorrect beliefs and results of exposure to a deception. So it's interesting that it emphasizes the fact that if I say John fell for the story, there is an implicit note here that the story was actually wrong. So this is how FrameNet handles those 2 meanings. Here's a quick comparison. ProcBank has word-specific meanings. FrameNet has meaning defined by situations. ProcBank has a small label inventory for semantic relations, whereas FrameNet has a huge label inventory because they are specific to the different semantic situations. But in ProcBank, the label meaning might not be uniform across predicates, and in FrameNet, they just aren't to begin with. Now, what is crucial for NLP are the following 2 points. ProcBank has a very good coverage of both verbs and event nouns in several languages, whereas FrameNet has an okay coverage for English and not much cross-linguistic coverage. And ProcBank has lots and lots of annotated text, and FrameNet has a very small amount of completely annotated text, and otherwise it has lots of annotated example sentences. So for these 2 reasons at the end here, NLP has been much more interested in ProcBank recently than in FrameNet because the data is much nicer. On the other hand, we liked FrameNet because it has this orientation towards situations as opposed to towards words. And at the company I worked for until last fall, called Elemental Cognition, we created an ontology Hector, which fused parts of FrameNet that were done and that we liked with an ontology for things that we took from the New Oxford American Dictionary. And this is work in progress. And I mentioned this to highlight the fact that NLP still doesn't have really good ontologies that it can use for all purposes. So now, in the remaining 3 minutes, I want to talk about some computational experiments we did. I will not give much detail, but it will perhaps give you a sense of how well we can do. So again, this is joint work with former colleagues from Elemental Cognition. So we did an experiment using what is called multitask learning. And multitask learning, so first of course, all natural language processing today is based on machine learning rather than writing handwritten rules. And the kind of machine learning we did is multitask learning. And in multitask learning, you have two different tasks that create two different models, but they are trained together at the same time. So when you're training them together, they can profit from what the other model is learning. And this, of course, makes sense if you suspect that these two tasks are related. And our two tasks are very closely related. So we did show that it made sense to do multitask learning. The input to the first task is a sentence and a marked trigger. And the output was the word sense of the marked trigger. And the input to the second task is the same sentence with the same trigger marked in the sentence, but with the frame name, the gold frame name. What is the actual word sense of this sentence? And then the output here is the roles and the spans for the roles. So the first task is word sense disambiguation. The second task is semantic role identification. And we're using here our in-house Hector ontology. And the architecture we use is an encoder-decoder transformer model using the T5 language model underlyingly. This is what the data format looks like. So this is what NLP people do. They take a corpus and create these sort of representations. Here is our first task. We call it the frame task. So we write down frame colon. Here's a sentence. This is a sentence from the actual corpus we were working with. Two of the cast fainted and most of the rest repaired to the nearest bar. So repaired is a word that's ambiguous. And in this particular sentence, it means self-motion. And note that we have these asterisks around the word repaired, and that indicates that we're asking the system to learn the meaning of repaired, not of any of the other words in the sentence. And then the second task, which we're training at the same time, is the arcs task. And here we plug in the fact that this is the self-motion meaning of repaired that we're interested in. So repaired is still has still asterisks around it. And now notice that we have these position numbers around all the words. And the output here is an identification of the spans and the roles for the semantic arguments. So the self mover is a span from 6 to 9, most of the rest. And the goal, and that is the self mover, who repaired, who moved themselves, most of the rest. And then the other question is, where did they go? What was the goal of the self movement? Well, that's 11 to 14 to the nearest bar. So this representation allows us to capture both the spans and the roles. And then these are just two more examples. Our architecture is we use a T5 encoder, and then we use two different decoders. One is a discriminative decoder that chooses the correct word sense in context, and that is for the word sense task. And for the argument task, we use a generative decoder because we can't simply choose, because we have to identify the span as well. And here are the results. In terms of identifying the meanings, we get a frame accuracy of 90%. So this is obviously trained on a training corpus, and the numbers I'm reporting are on unseen test corpora. And these are freely occurring texts, newspaper articles, or sentences from the British National Corpus. For the roles, we do slightly different, worse. I don't want to explain the meaning of precision recall and F1 measure, but 84% gives you a rough sense that roles are more difficult than word sense disambiguation. And to finish off, let me just mention we used our architecture on standard ontologies, exactly the same setup, but now we're testing on PropBank and FrameNet, which I introduced to you earlier, and we compare against state-of-the-art systems. And you see that for PropBank, we got a small improvement, whereas for FrameNet here, we got a small improvement for word sense disambiguation, but we got a massive improvement for role prediction. So why is that? PropBank has been undergoing a lot of development in NLP. I mentioned that it is favored in NLP. So a lot of work has gone into prop bank. So that's why overall prop bank performer is better. And FrameNet has received less attention. But I want to emphasize that while our results here are sort of very close to the state of the art, even though we beat it, these efforts, He et al. And Li et al., are based on ad hoc systems for prop bank, whereas our approach is a generic semantic approach that we developed for our Hector ontology, and then we applied it to this prop bank data, and it did well. So we were happy about that. So summarizing this section, our T5-based multitask approach beats the state of the art, and it is much simpler. There is no ad hoc neural architecture for the task. There's very little parameter tuning, which is a big deal in neural NLP. And an interesting little detail, we did a detailed error analysis, which apparently hadn't been done in the literature before. And a very good portion, a quarter to a third, are actually errors in the gold standard. So let me conclude this talk overall. First of all, I hope to show you that it is a very long way to deep text understanding by computers. And we are right now in natural language processing at the point where we need to define what we mean by deep text understanding. And we need to start evaluating systems so that we can actually start thinking about how to get to deep text understanding, because no one really knows what it means so far. Now, if you remove understanding any inference between sentences and a text, just look at a sentence level, we're only starting to cover the full range of meanings we need to access. I went through this list of aspects of sentence meaning, some of which are so far completely ignored by NLP, some of which are ignored by linguistics, I should add. Now, let's narrow it down again to semantic parsing. That is this question of who did what to whom. We have good resources, and therefore we have pretty good results. So resources means annotated corpora. However, more work is needed. In general, we need to understand what the linguistic resources we are using actually are encoding. And I'm saying that more oriented towards our NLP colleagues who often just use the data without really understanding what a prop bank annotation or a FrameNet annotation is. And let me just mention my personal goals at Stony Brook are to continue working on the Hector ontology and on semantic parsing, but in particular also expand this work I mentioned on cognitive state detection. So thank you very much. And I have some additional slides. If you have specific questions, I'm happy to take questions.
Thank you, Owen. I think what we should do is see if people want to put up their artificial hand or their real hand and ask anything, or you can, of course, you can put a question in the chat, but we will try to get you to turn on your microphone and ask it. Anything on people's minds?
Asma?
Asma, please.
Okay, so it's related, my question is related to NLP as a discipline. Like I'm confused between going for cognitive aspects of linguistics and NLP. When I see it, they are both interesting, but NLP has more scope, I've heard, in the professional life, and the salaries are higher, etc. So should I pursue this course in PhD?
Yes, that's a very good question. And you know, you have to choose your goals for yourself personally. As we all know, there's been this boom in commercial natural language processing. The products that we have access to have gotten much better in the last 5 to 10 years. So for instance, I don't know, I think a lot of us probably use Google Translate, right? It's you go to translate.google.com, you enter stuff. It's really kind of amazingly good, actually. And for many years, so I'm in Germany, I speak German. For many years, I would trick Google Translate with German sentences with weird word order and so on. It would get confused. It no longer gets confused by weird word order in German sentences. So there's been a lot of progress there. And because there's all this progress and people are interested in, talking to their phones and talking to their thermostats, and companies are interested in automating their customer service and so on and so forth, there's a huge need for people who know how to do natural language processing in industry. So that is why there are high salaries right now, which hasn't always been the case. When I got my PhD, there were very few industry jobs. So that's exciting. But on the other hand, a lot of NLP, as I try to convey, is based on, here's some data set, let's choose a machine learning method, let's evaluate it, and we're done. There's often not enough time to really ask what's going on here. What is a linguistic phenomenon that the data set captures? What is a model learning that can be very hard to understand for a deep learning model, and so on. So if we're the type of person who like to build things, then NLP is great. If we're the type of person who likes to understand things, take them apart and really get to what's happening deep down, NLP, especially in the commercial world, can be a bit frustrating. So I was very lucky when I worked in industry for 3 years before joining Stony Brook. The company was very research oriented, but that is not typical. So I think therefore, Asma, you would have to determine, what is more interesting to you, economic ease or intellectual satisfaction. I don't mean to say that NLP is not intellectually satisfying. I take that back. It's just that you're satisfying different parts of your intellect. The intellect that wants to build versus the intellect that wants to understand.
Somebody told me that NLP involves programming,
yes.
and I was a bit scared of that. Is it hard? Because I did learn C+ language in A levels, and I found it to be very difficult. Now I'm scared of that.
If you're scared of programming, don't go into NLP, to be perfectly blunt. Sorry to be so blunt, but yes, you need to program, and the NLP isn't about programming, but programming is kind of the tool. The way for a theoretical linguist, writing is a tool, right? That's how you show that you've done something. You write a paper, and if for some reason you're unable to write papers ever, you shouldn't become a theoretical linguist. And same way, if you just don't ever want to write a program, you shouldn't become an NLP person. Yes, you will be doing a lot of programming. It's just sort of the tool that you use.
Thank
I
you.
apologize for being so blunt, but
It's all right. I needed an honest opinion.
okay.
Thank you.
Anastasia?
Yeah, thank you. Thank you very much for this amazing talk, because I've recently been engaged in making the corpora and also working with the gold standards and trying to work this word-to-word alignment on parallel corpora with our group. And so I'm actually more interested in the in your personal goals that you talked about, that you want to expand this work on cognitive state detection. I'm like, for my research, I'm working with the metaphors. And when I was doing research, I actually came across one problem, that in many corpora, it's not possible to find metaphors other than just by going like manually through every sentence that you have in a corpora, or just like skipping them through. Is it somehow like close to what you want to achieve, like to create a kind of algorithm that the machine in natural language processing will detect those metaphorical meaning by itself? Or is it somehow, have you, like, the second question here, have you also seen some papers that are now available? I know that there is one group in Amsterdam, they are doing this metaphor detection, and they have a tool basically how to detect metaphors in corpora. Or is it something that you're not touching?
Yeah, so metaphors is a really interesting area, and it relates to a lot of parts of NLP, and we humans do use a lot of metaphors, and I have not worked on it at all. And it does relate to cognitive states. So for instance, our sentiment towards something can be expressed by the choice of metaphor. But it is just something I have not worked on, and I know there have been several research programs in the US oriented towards that. In general, about corpora, I do feel like that it is necessary at some point to go through corpora and identify things by hand, because that's the data, that's understanding what actually happens in language. And corpora are important for NLP and for computational linguists, but also for all linguists, right? Because corpora represent language use, and they represent the empirical subject matter that linguists deal with, which is language, human language. And in order to understand a phenomenon, a good way to do it is to annotate a corpus. And corpus annotation, you start out with some idea what you want to annotate, and you do a little bit of annotation, and then to annotate, and you train the annotators, and then the annotators come back and say, look at this sentence, what you told me to annotate, it doesn't make sense, it doesn't work here. And then you realize, oh, the phenomenon is more complex, and I need to introduce another aspect to the annotation scheme. And this way, the process of developing an annotation manual itself that you can give to annotators and have them annotate a text is a scientific contribution, because it represents an exploration of what the scientific phenomenon is you're trying to annotate in the first place. So I'm a great fan of corpus annotation and taking it very seriously, and taking the resulting annotation manuals as a major contribution. They're essentially bits of descriptive linguistics, which you can then run with, and you can do NLP with the resulting corpus, or you can use it for theoretical linguistics. But it's sort of this initial conceptualization of what the problem is that I think is extremely important.
Oh yeah,
Sorry.
you started talking, yeah, thank you. You started talking about annotation, and annotation is for sure, it's like it has to be done manually. But as a person who's working in NLP, do you think that there will be a way in the future that this annotation of metaphorical meanings or metaphorical usages, it will be possible to be done by the machine itself, already pre-trained, or some golden standards or not, or it's still impossible?
Yeah, I think basically, yes, it will be possible. I think metaphors are particularly complex. So it's not just a matter of annotating a big corpus with metaphor information and then learning a model. I assume there's more. And it's just an area which I don't happen to know much about. So I'll just sort of not say anything more so I don't say something stupid. So I apologize for not being able to address metaphors specifically, but
oh no, thank you very much, because what you already answered, it actually touched on my questions that I had. Thank you.
Let's see, Chung, I think you were next.
Oh, hi, Professor. So my question is based on your experience, what is the role mathematics is playing in NLP or computational linguistics? So it's to prepare for all those years I've been a humanities student, but now I decided to study computational linguistics. So I need to, take lessons in probably. So now it's I'm taking 2 programming courses at Stony Brook University, and I was told that mathematics is also playing a critical role in this industry. So I also signed up for a statistics class. So do you think this is a right choice?
Yes, I think it is a right choice. So I see programming as sort of a basic tool that you definitely need an NLP, no question. I was sort of definite about that. I actually think you need it in many, many disciplines, and more so in the future. Well, I won't get on a soapbox and say that, but I think basically everyone should know a little bit of programming, because it just can automate tasks. It's like word processing, right? Everyone needs to know word processing nowadays. Programming, I think in 10 years will be considered like word processing. It's just, and there are different levels. Programming doesn't always mean that you write a completely new system which controls the moon landing. It can just mean you write a little script that can search for something in in a bunch of files or something. So programming is sort of elemental. Mathematics is important, and I think in at least two ways. One is machine learning has become so massively important, and some of NLP is about changing existing machine learning approaches. In order to do that, you need mathematics. You need this statistics background, linear algebra, those sort of things. That is actually not something I have a strong background in, even though I was many years ago a math major in college. But people who have a strong background can make contributions to machine learning and can contribute in a more deep way. So I think taking a statistics course in particular, which underlies so much of machine learning, is definitely the right way to go. The other way in which mathematics plays a role is a more theoretical aspect of computational linguistics, not engineering NLP, but the formal study of formalisms. And there we need to have mathematical concepts from various areas, not statistics, but discrete mathematics, in order to characterize, say, the formal power of different types of formalisms. So if that's something you're into, then you also need that sort of mathematical background. But if there's a choice of a programming course or a math course, I would say take the programming course, because that is just fundamental if you want to do anything in NLP. You need to just be very at ease with programming.
Let me just, before we go to the next questions, Owen, is it okay if students contact you with, with such questions about, these areas if we don't get to everybody? Okay.
Absolutely.
So
yeah.
can we put your email in the chat so that people are sure to have it? We'll also post your slides later if you're okay with that. But if you can put the email in the chat, or is it just owen.rambow@stonybrook.edu?
Yes, it is. Yeah.
Okay, I'll do it right now. And let's take the next question. We're going to have to wrap it up relatively soon, but I see a couple more. So let's do those for sure.
So Maggie, I think you've had your hand up longer than Maggie, me.
Yeah, that's fine. Yeah, thank you for the really fascinating talk. So I'm currently a undergrad student, and I'd say a corpus linguist by training. But I'm really interested in sort of computational linguistics and NLP, which is kind of the reason why I went down the route of corpus linguistics. But I was basically wondering, because in my home university, the people who do NLP are all the computer scientists, not the linguists. And I'm kind of at a crossroad myself. And my sort of perception of the two fields, so computational linguistics and NLP, is that with computational linguistics, like you said, you're sort of, rather than just building things, you're trying to, after you build something, you're trying to sort of unravel the phenomenon about language. You're trying to delve deeper and solve the actual problem. Whereas with NLP, it's just, to me, it just seems like a bunch of computer scientists building, the next Alexa or the next Google Home. Yeah. So I'd really like your advice on sort of areas that's a good intersection between these two fields. And possibly if you have any sort of readings or materials, I'd be really keen on sort of getting to those. Yeah. Thank you.
Well, what is your home institution, if I may ask?
Lancaster University in the UK.
Yes. So there are several universities where there are people in linguistics departments who are doing computational linguistics and NLP. And I would like to push our own university, Stony Brook University in New York, where we have a group of 5 now computational linguists in the linguistics department. And it is a major emphasis. And there's a special master's program in computational linguistics, and all of us are in the linguistics department because we are either we are linguists, except in my case, actually by training I'm not. I'm a computer scientist, but I really am interested in linguistics. I mean, in language. The reason I'm doing NLP is not because I'm interested in machine learning. I'm doing NLP because I'm interested in language, and being in the linguistics department, sort of feels like finally having found my real colleagues after dealing with computer scientists a lot. And machine learning is an absolutely crucial tool. we couldn't be where we are right now. And it is important for people in NLP, but also computational linguistics to understand machine learning. And there have to be people who are really advancing machine learning. That is absolutely crucial. But that is not me. That is not what I'm interested in, and it's not where my abilities lie. So, so I think there are several schools where there are a lot of NLP people and computational linguistics people in linguistics departments. So in the UK, there's Edinburgh, I think, would match that criterion. In the US, there's us, Stony Brook, but University of Washington, NYU now as well, and several others, Ohio State. I apologize, I'm sure I'm missing some. So I think sort of going for that area. And when I was doing my PhD in the 90s at the University of Pennsylvania, there was a very close cooperation between the linguistics and the computer science department. I've been told now at Penn, for various reasons, that close cooperation has drifted apart again a little bit. But when we were there, where the grad students sat, was mixed. There were linguists and computer scientists sitting next to each other. I got a master's degree in computer science. Other people who are getting a PhD in linguistics would get a master's degree in computer science, like Rajesh Bhatt, who I think is giving a course. So you might want to ask to what extent there is communication between the two departments.
Sure. That's great. Yeah, thank you.
I hope that helps.
I actually have another question regarding like the methodology of your the experiments you mentioned, and the evaluation, the implementation of the evaluation. But I think Vincent had another question, so I don't want to sort of hold up the.
I had another question, but I could just contact you by email.
That's
if
true.
That's better. Yeah.
We might actually see each other in person at some point too.
Finally.
So Maggie, why don't you go ahead with your second question?
Yeah, and let's have Maggie's now be the last question.
Okay, sorry, yeah.
That's absolutely fine. Other people can contact you by email, but absolutely, Maggie, go ahead.
Sure, cool, thank you. Yeah, so I'm quite interested in sort of how you implemented the evaluation part, and also, just your general methodology when you were talking about like semantic parsing.
Yeah, you mean the evaluation part of the deep story understanding? Challenge, yes. Okay, so here's, I'm going to make this very short because there could be a lot to say. The truth of the matter is we haven't, because it's hard. So what we did is the record of understanding that we're proposing is written. It's English language description of the knowledge needed. And our idea was that we could take that we would require systems to output a similar kind of record of understanding, but it wouldn't have to be identical to ours, of course. And then we would use some technology, existing technology, to match whether the output actually corresponds to what we say the output should be. But then, of course, we're using NLP to evaluate NLP, and that has problems with it. On the other hand, this problem is very similar to the evaluation of text summarization, which has been an NLP area for decades. And in text summarization, it has this property that you can write different summaries that humans will say, these are good summaries, but they only intersect in content. It isn't the case that humans always agree on a good summary contains exactly this content. So methods have been devised to evaluate machine summaries, so that they can take into account that there's this intersection thing. And this evaluation of summarization has been partially also automated. So I see this problem as being very similar to the evaluation of summarization, which has been tackled at a very high level because it's a very prominent NLP problem. And so I believe there are solutions in that direction.
Wow.
So
yeah,
that's
really interesting.
slightly hand wavy, but that's sort of the executive summary.
Okay, cool. Yeah, thank you for that.
Thank you all. Owen, thank you so much. I don't know what you decided about whether you were going to eat dinner before the talk or after the talk, but if you haven't had it, you certainly, I'm sure, will enjoy it now.
I'm going
I know it's
straight
late
for a
evening
drink
over
now.
there.
Yes.
Yeah, thank you so much, Owen. Let's give a big virtual round of applause, those of us who are left.
Thank you.
And everybody feel free to be in touch with Owen with any further questions. We'll have a recording of this, and the slides will be available for everybody who missed it or would like to see it again. And have a nice weekend, and see everyone next week.
Thank you.